Hello, everyone. In this video, I'm going to talk about this case of homogeneous linear equations with constant coefficients under the idea of looking for the solution of higher order linear differential equations. So if you remember all the other videos, we worked on second and first, mainly second order differential equation. So here, after we looked into singular points and different techniques, and we saw auxiliary equation or characteristic equation, we saw distinct roots, repeated roots, and all that. So I think the goal here in this is to explore some examples based on what we learned in previous sections. And of course, our interest here is to help understand why these techniques work. So this is done usually using an operator approach. This technique is kind of useful in tackling many other problems in analysis, such as solving partial differential equations. So it probably depends on your track. Take a little more math courses that deal with partial fraction um, kind of partial differential equations, right, and solving them. Usually, we talked about linearly independent solutions. So if we have them, and the operator is just going to be a combination of these linear independent solutions. But here, instead of going through the kind of the theory, which you can see in previous section, I'll just do some examples for you, and just so you see it builds on what we did, and it kind of runs smoothly pretty much. It's not that complicated. All right, so let's, for example, if you have distinct roots, what would you expect? If you have distinct roots, you would expect that the auxiliary equation has real distinct roots, then the end solution, these independent, let's say the solution y1 of x is going to be has this part which we've seen, the exponential part. And the other linearly independent solution is going to have R2x, where of course R1, R2, and so forth are these distinct roots. So you'll have 2y sub n of x equal exponential to r sub n x, which means you can combine these in the general solution, which is y of x, and using these arbitrary constants. So this kind looks familiar, right? Let's do an example. If I have, you see, now we do a third order, and minus do a second derivative. Let's say minus 5 times the first derivative. And here we're solving, it's not an IVP, just more of find the general solution. So the auxiliary equation will be this way. And here, if you run into this and you're not sure how to solve a third order, often you can use factoring, then you'll have a second order, then you can use still factoring quadratic formula to solve. But if you run into this, you would remember something you've done in pre-calculus or maybe even in calculus Uh, so, all these theorems, the factor theorem, the remainder theorem, the rational zero theorem, all that stuff. Or you can do by inspection. You can just try, um, you have six and this is one. So 6/1 and other factors, you'll have a bunch of numbers you can try. So by inspection, you can have we find r equal 1 is a root. And once you find the first one as a root, then you can now divide. You can now use, let's say after that, we use long division or even synthetic division, long division, to find the because r minus 1 is going to be a factor. So if you do long division, you're going to find the quotient to be r squared minus r minus 6, and the remainder, of course, to be 0 because, excuse me, because r minus 1 is a factor, so the remainder will be 0. So that tells us that r cubed minus 2r squared minus 5r plus 6 now changed to this r minus 1 times r squared minus r minus 6, which can be further factored to r minus 1 times r plus 2 times r minus 3. And that would give us the roots. R sub 1 is, let's say, 1 from the first one. R sub 2 is, let's say, -2 from the second factor. And R sub 3 is equal to from the third factor. And now you can just set up the general solution using this arbitrary constant with, so 1x, let's say negative here 2x in the exponential, and okay. So it's not bad. So let's do another example. Let's say a similar example, but you don't have to go into long division. Um, I will abbreviate this one. So let's say find general solution of, let's say, this. All right. So what do you think you're going to do? The auxiliary equation, right? Here you have, so r cubed plus 7r squared minus 2r. You see that r is a common factor. So r squared plus 7r minus 30 equals 0. Then you factor and you find you have three distinct roots, and you put them in the general solution. This one gives you 0. So and these two here will give you 3x and negative 10x. Then this becomes that. Okay, so we could go into, so distinct roots. We may have complex roots. And as we saw in the past, we would use, if you're running to, let's give what we did something in the past, like, of course, these are the, let's say, is a complex root of this auxiliary equation. Of course, alpha and beta and are real. Then so the complex conjugate, of course, is going to be this. They come in conjugates. Then we can set them up, but just to give you, of course, because we've done this in the past. So the two linearly independent, based on, let's say, these, you'll have, and that's where we use the cosine and a sine. So let's maybe do this in example. And let's say we have third order and we get this. Then we set it up, the auxiliary equation, and then you know what you need to do with that, and you factor and you get this. Then now the first root is 1, it's a real one, but the second root is the from this second order part is going to be a complex one. When you solve, you find that it is um, complex, and that gives you, of course, the conjugates. All right, so now I'll keep it in the same picture. So same here. So what is the general solution? The first one came up to be real. So the first constant times the exponential with r sub 1x. But the next one is going to be with the cosine. So negative 1 with x, because that's alpha and that's beta. That's alpha, that's beta there. And cosine 2x, then plus c sub 3 um, exponential with negative alpha x and sine of beta x. All right. Let's. So what if we have repeated roots? Similar work we can investigate, but what will happen is you will have this type of linearly independent solutions, just like we've seen in the past. Then with alpha x sine of beta x, x e to exponential to alpha x sine beta x, and keep going. All right, let's give you example. Let's pick this fourth order. So the auxiliary equation gives us this. Then you're like, how do I solve this? You've done in the past. Some of these even show up in college algebra, where they use substitution, and this becomes now u squared plus 4u plus 4 equals 0. Then this we have, so it gives us kind of the root. So now back substitute r squared equal -2, r squared equal -2, which means r is plus or minus square root of negative 2, r equal minus plus or minus, let's say this y r sub 1 and r sub 2. Square root of 2, and r sub 2 is plus or minus I times square root of 2. So that tells us that we have complex roots, and alpha is 0. So alpha here is 0, right? And beta is square root of 2, which that will make the exponential part go vanish in the solution. And we just set them up. So while the general solution is just going to be, let's say, the first arbitrary constant times cosine square root of 2 times x. You remember here, it's that which is gone, plus 1. All right, so second, you will use x times cosine square root of 2x, right? So now I'm just leaving this. Let's keep building it. Now with sine. All right. So I think if we have, of course, alpha not be 0, then you just have, for example, the first constant times exponential. Let's say alpha is 2, then you'll have exponential 2x, right? Times cosine, and let's say beta is 1, then 1x. So something like that. So that's not an issue. That concludes this part. Thank you.